Hello and welcome to today's video on nucleophilic substitution. First, I want to define what a nucleophile is. A nucleophile is any species that possesses a lone pair of electrons that is capable of donating a pair of electrons to an electron-deficient centre, forming a dative covalent bond. Examples of nucleophiles are OH-, the hydroxide ion, and ammonia. Both of these species possess a lone pair of electrons and they essentially act like donors to an electron-deficient centre, forming a dative covalent bond. Notice, nucleophiles are usually fully negative ions like the hydroxide ion, or they have strong partial charges within a molecule like ammonia, and we show these using partial charges. In particular, halogenalkanes undergo nucleophilic substitution reactions because they are saturated molecules with polarity within them. Saturated means all the atoms are linked by single bonds and the compound does not contain any double or triple bonds. Looking at the halogens such as fluorine, chlorine and bromine, we know from their position in the periodic table that they are very electronegative, and what is important in halogenalkanes is that they are more electronegative than the carbon atom. This means that in a carbon to halogen bond, there will be an inductive effect, meaning the electron pair will be displaced towards the more electronegative halogen atom. The presence of an electropositive carbon centre means halogenalkanes are readily attacked by nucleophiles, which have that lone pair, which they are capable of donating and forming a dative covalent bond with. Since there is polarity in the carbon to halogen bond, and the electrons are displaced towards the halogen atom, we will expect the bond to break heterolytically, therefore meaning the halogen atom is replaced by another atom. Heterolytic bond fission occurs in halogenalkanes like we've just covered, and this is due to the bond polarity and the electrons being displaced towards the more electronegative atom. Because of this uneven distribution of electrons, we expect the bond to break asymmetrically, and both the bonding electrons are transferred to the more electronegative atom, as we can see in A. Next we'll be looking at two of the main substitution reactions, alkaline hydrolysis and elimination reactions. Both of these reactions have specific conditions which are essential for the reaction to occur. Starting with alkaline hydrolysis, this is the conversion of a halogenalkane to an alcohol. The conditions required are: you must use aqueous potassium hydroxide solution. The hydroxide ion from this is the nucleophile for the reaction. The reaction should occur at room temperature or with very gentle heating, and a small amount of alcohol should be added as a neutral solvent. In this reaction we are using a halogenalkane, specifically 1-chlorobutane, and the reaction involves breaking the carbon to chlorine bond heterolytically. The two electrons from the bond are donated to the chlorine atom to form Cl- with a lone pair. The hydroxide ion then forms a dative covalent bond to the functional group carbon of the halogenalkane, essentially substituting the chlorine atom. In this drawing, you can see a transition state that represents the species that has the highest energy state along the reaction pathway, and it appears at the top of the activation energy hill on a graph. You can see the dotted lines showing bonds breaking and forming. This is an SN2 reaction, also known as substitution bimolecular, and as you can see in the drawing, the spatial arrangement of the product molecules involve an inversion of configuration. So, looking at the first species, the hydroxide has taken the place of the chlorine, but the molecule has been inverted, and the Cl- ion is left on its own, which will likely react with another species. An extra point: I have included the rate equation. Both species, the hydroxide ion and the halogenalkane, are first-order reactants, so both can change the rate proportionally when concentrations are changed. Finally, we will look at the elimination reaction of halogenalkanes to form alkenes. The hydroxide ion, again, is a nucleophile for this reaction. There are specific conditions for this reaction that are required. Sodium hydroxide solution must be used in an alcohol solvent and it must be done under reflux. Reflux is the continuous boiling and condensation of a liquid mixture. The hydroxide ion attacks the bond highlighted between the two carbon atoms and it accepts a proton off the second carbon from the end carbon that is connected to the chlorine. The bond between the carbon and chlorine is broken heterolytically, leaving a chlorine ion, and the hydroxide ion has accepted the hydrogen to become water, which is also a product, and overall this leads to the formation of a double bond and hence an alkene. Overall, this video has reviewed the main processes of nucleophilic substitution. I hope you enjoyed.